Swayam Prabha. Digital India. Educated India.
So the focus for today's lecture is going to be somewhat, the content that we are going to be covering is going to be somewhat more advanced, most very topical. In fact, we are going to be looking at some of the results that first came on 2016. So which is more about some advanced results on PL inequality, and we will be using those results for showing the robustness of the optimization algorithm that we had looked at in the previous class. So just to quickly recap, so we started looking at this notion of finite time and fixed time stability, and we looked at this particular rescale gradient flow, which was defined as x dot is some with p greater than 2, and this was shown to be finite time convergent. In fact, we looked at the Lyapunov characterization of finite time stability of equilibrium, and so if I look at the Lyapunov characterization, so if your Lyapunov inequality or the time derivative of the Lyapunov function satisfies this particular inequality with alpha being a number between 0 and 1, then you can show the trajectories they converge to the equilibrium in a finite amount of time, which is dependent on the initial condition x naught, and that settling time function is actually upper bounded by c times 1 minus alpha. So this was finite time stability. We can also talk about fixed time stability of such equilibria if the Lyapunov function satisfies inequality of this form C1 v to the alpha 1, C2 v to the alpha 2 with alpha 1 between 0 and 1, alpha 2 is a number greater than 1. So this you can show is in fact now fixed time convergent, meaning that the settling time function is independent of x naught, and this is going to be upper bounded by 1 over C1 1 minus alpha 1, right, and this is for fixed time stability. Yes, thanks for pointing that. So this should be V naught or V of x naught. Okay. Yeah. So this is V of x naught. All right. So, and as I said, this is nothing but reparametrizing your simple gradient flow. So in terms of trajectories that your x1 and x, let's say x is 2 dimensional. Okay. Let's assume x is 2 dimensional. So you have x1 and x2, and let's say origin is the equilibrium or optimal solution. So if your gradient flow, it's starting at some x naught, if your gradient flow let's say follows this kind of trajectory, so the path that is traced by the by this particular dynamical system, or path that is traced by an equivalent dynamical system where you have fixed, you have the notion of fixed time convergence, it's going to be exactly identical. So it's basically we are accelerating the speed, we are essentially accelerating along that path. So we are changing the speed with which we trace this path, but the path is going to be exactly the same, that path traced by it. As a function of time, x1t and x2t would look different obviously, but if I look at the path traced by this particular dynamical system, this is going to be the same as the path traced by a nominal gradient flow without normalization. Okay. Or let's say if I look at this, a simple gradient flow like this, so let's call this 1, a finite time convergent flow which looks something like this, with p greater than 2 and let's call this 2, and a fixed time convergent gradient flow p minus 2 p minus 1 minus with p greater than 2 and q is a number between 1 and 2. So, all these 3 dynamical systems, they are going to trace the same path. So, it's just that you are doing curve reparameterization. So, essentially what you are doing is you are changing the basically you are sort of changing the coordinate system, and in the transformed coordinate you are converging, maybe you are running this new gradient flow, right. So, essentially you converge much faster, and essentially you change the speed with which you trace this path, but the path that is traced by all these 3 dynamical systems, these are going to be exactly the same. Okay. Yeah, that would, yeah, any scaling would be the same, though not when once you discretize it, that may not be the case, right, because you are then sort of like you are talking about discretized updates. So, that may not be the same, but in continuous time they are going to be the same. No, because like let's say for the discretized one, from after this point, the update, like for the same step size, the simple gradient flow would suggest an x which will be somewhere over here, whereas maybe a fixed time gradient flow would suggest an update which is somewhere over here, right. And so they won't be like the path trace there would not be the same, because it's because due to the discretization, but in continuous time they would trace the same path. Yeah. Okay, so that's another question, that what kind of guarantees can we provide once we discretize these fixed time convergent gradient flow. So, well, the guarantees are not of the form of that, like for instance with gradient flow, when you look at gradient descent for L smooth function, we had a specific characterization of the step size which was in 1 over L kind of step size, right. We don't have that kind of interesting bounds on the step size, but the kind of guarantees that you can provide is if so the kind of results that exist is if the function admits a quadratic type of growth, at max quadratic growth, then if I look at this particular discretized step, let us say step size eta, scale. So, this is basically the discretization of your fixed time convergent gradient flow. So, the kind of results or kind of guarantees that we have is there exists a small enough step size such that independent of the initial condition, you like one x would converge to an epsilon ball around x star in a fixed number of iterations. The kind of guarantees that we can provide are only of existence type. So, there exists a small enough step size such that even the discretized flow or the discretized fixed time, like the discretized version of the fixed time stable gradient flow, because in discrete time you cannot talk about exact convergence to the optimal solution, right, and you can talk about that in continuous time, but in discrete time even maybe as a result of discretization you may just slightly overshoot your x star or undershoot your x star and so on, right. So, if you fix an epsilon ball around your x star, you would converge to that epsilon ball no matter where you start, you will converge to that epsilon ball within a fixed number of iterations independent of initialization, but what would be the bound on the step size and things like that, that is still an open problem. So, all we have is the existence type result and not the bound on the a specific bound on the step size. Okay, so that's, I mean, that's where the current sort of state of the art is.
We also don't know the number of iterations.
Yeah.
In that we want to bound on the time.
Yeah. So
Here depending upon theta.
yeah, so we do not know that. The number of iterations as a function of theta, we do not know that. Mm-hmm. Yeah. Right. Yeah. So in fact, if you have a dynamical system whose equilibrium is exponentially stable, you can potentially make it fixed time stable by changing by this kind of normalization. So if you have for any dynamical system that is exponentially stable, this can be achieved. So you just have to do the normalization, and that would make that particular equilibrium fixed time stable or finite time stable, depending on what kind of normalization you end up doing. Okay. Let's say we are going to be working with, so we want to design a gradient flow, a rescale gradient flow, which is fixed. So let's call this, let's give it a name. We'll just, from now on, we'll call it FXTSGF, which is fixed time stable gradient flow. Okay. Let's see. Okay. So suppose I want to design a fixed time stable gradient flow for, so we assume F is strictly convex. So in the last lecture, we looked at the case when F was strongly convex, right? And we were able to design a fixed time stable gradient flow for that. But what if F is strictly convex? What kind of algorithm would work if F is strictly convex? Or let's say F is strictly convex such that Hessian of F is positive definite, right? So the question is, we want to design a gradient flow which is convergent in fixed, which converges in a fixed amount of time. So in the previous lecture, we looked at the case when F was strongly convex, mu strongly convex, and we were able to, when F was strongly convex, we had this particular gradient flow, right? Simple P minus 2 or P minus 1. Okay, and we showed that this was convergent in a fixed amount of time. Now, if F is strictly convex, how can we modify this? Yeah, basically Hessian inverse, right? The same we did, the same thing that we did with the simple gradient flow, right? So when F is strictly convex, so we are now going to be designing a new type of gradient flow, which is going to be, again, everything is inspired from simple gradient flow, and then so the equivalent modification of the Newton's flow, or which is of this form. Okay, and let's see if this works. So when we have strictly convex function, what would be a good choice for Lyapunov function? What is a good Lyapunov candidate for that? Half this thing, right? Because once you start differentiating it, you will get Hessian, and you have an Hessian inverse sitting over here. So V dot is essentially transpose Hessian times X dot, right? And X dot is now Hessian inverse times this. So Hessian inverse, that becomes identity. So what you are left with is V dot is negative Okay, is this clear? So this would mean that I can rewrite this as, so 2 minus the same, exactly the same approach. So this would turn out to be, right, and similarly 2 times q over 2q, right, and this is nothing but minus 2v p over 2p minus 1 minus 2v q over 2. Okay, and for the specific choice of p, when p is greater than 2, p over 2p minus 1 is a number between 0 and 1, and for q between 1 and 2, this would be, this exponent would be the number greater than 1. So essentially we are in, so that basically ensures that v dot is essentially less than equal to certain thing. I mean, if it is equal to, you can always write the, like, I mean, write this as less than equal to, and you recover the. So let's call this to be alpha 1 to be p over 2p minus 1 and alpha 2 to be q 2q minus 1. So what you have here is 2 to the alpha 1 v1 alpha 1 minus 2 to the alpha 2 v of alpha 2, right. So this satisfies the with alpha 1. So alpha 1 is a number between 0 and 1 and alpha 2 is greater than 1 for these choices of p and q, and therefore that means this is fixed time convergent with settling time t less than or equal to 1 over 2 to the alpha 1 1 minus alpha 1 plus 1 over okay. So for strict, like whenever you see strict convexity with Hessian positive definite, it makes sense to use Newton's type of flow or a modified Newton's flow, okay, like this. So that, I mean, this is basically an accelerated version of the same Newton's flow that we had looked at in the previous class. Another interesting thing to observe is, let's say I am looking at this particular optimization problem and I have a specific budget on how much time we want to allocate to solve this particular optimization problem, right. So I can choose my p and q in such a manner so that I basically come up with a bound on the time it is going to take to converge, right. So it is not just fixed time optimization, it is also like predefined time optimization. So if you give me a bound that you want to solve this problem in this much amount of time, you will accordingly choose your alpha 1 and alpha 2, that will actually ensure that the settling time is upper bounded by that particular time, and therefore you are guaranteed to converge in that much amount of time, right. So this also, if you have a budget on time, so it also sort of specifies budget on total time required to solve the optimization problem. For fixed time now, right. So once you have these two, so that's the difference between finite and fixed, right. If you have a gradient flow like this, then it depends on the initial condition, but if you have a gradient flow like this, then you make it independent of the initial condition. Yeah.
So when we convert this to distance, so will the numerical stability be affected by the choice?
Yeah, definitely. So that's why I said, like, I mean, you have guarantees in like when you discretize it, but the guarantees are only of the existence type. So for small enough eta, this would still hold, but how small the eta should be, specifically if, like, even if let's say f is strongly convex and L smooth, can we still specify eta in terms of mu and L? That is also an open problem. It also depends on, but then for the, at least for Euler, Runge-Kutta, all these standard discretization, this result sort of holds true. Yeah, that there is a possibility that using symplectic Euler you can possibly make it work, but in fact, if the system is homogeneous, as in like 0 is the like x dot is of the form x dot is a negative x. So I mean that wouldn't. So for instance, if I am trying to minimize x square, I mean, I obviously know the optimal solution, which is x equal to 0, but the corresponding simple gradient flow would be x dot is negative x or negative 2x, whatever, right? But this is an example of homogeneous system. If I am trying to minimize x dot, I mean something like x minus 1 whole square. So x dot is negative of x minus 1, and that is a non-homogeneous system, right? So in general, I mean, for optimization it doesn't help, but if you are looking at just at the stability problem, forget about the optimization problem. If you are looking at the stability problem, if you have a homogeneous vector field to work with, then in fact you can specify this eta. You can specify the number of iterations as a function of eta, but only for the homogeneous system. It doesn't help us in the context of optimization, but in the context of stability, if you have origin being the equilibrium, then you can actually specify the amount of iterations it would take to converge to an epsilon ball around the origin. So only for homogeneous vector field you have explicit bounds, but otherwise, I mean, the bound of on eta is, I mean, that's an open problem for non-homogeneous fields.
So there's a cost function that can be vector field as well.
No, vector field, no, vector field in this case is always a gradient, right? Negative of gradient is the vector field. So x dot, whatever is there on the right hand side is your vector field. Cost function is always f of x. So obviously, I mean, since it works for strongly convex function, you can also extend it for functions that satisfy PL inequality. So we have been talking a lot about PL inequality, but what does PL inequality really imply? Okay, and this is again one of the seminal results from Karimi in 2016. So if a function, and the result says if a function satisfies PL inequality, then it admits at least quadratic growth. So I will tell you what this means. Let us say there is a function f that satisfies PL inequality with exponent mu, with modulus mu greater than 0. Okay. So that means f of x minus f star so it is lower bounded by a quadratic function which grows quadratically. The function has at least a quadratic growth is what this particular result says. Is the statement clear? So if the function growth is at least quadratic if function f satisfies PL inequality. And for strongly convex function, that was in fact the key point. Like if you are working with strongly convex function, even when you are close to optimal solution, because of this quadratic growth or at least quadratic growth, you always have non-vanishing gradients, or you have big enough gradients to converge faster to the optimal solution, which isn't the case with strictly convex functions, for instance, right? So, and the fact that most of the results that work for strongly convex functions also extend for functions which are potentially non-convex, like the functions that satisfy PL inequality. That may also have to do with the fact that I mean, these functions also admit some kind of quadratic type of growth. So let's try to derive this. Okay. So we know that f satisfies PL inequality. Okay. So what does it mean? F need not be convex. This can be an invex function. Any invex function, like some function that satisfy PL inequality are called invex functions. So f need not be convex. Yeah. So if PL inequality is satisfied, like I mean, if a function satisfies PL inequality, you only have two options. Let me just write this, and this will also be clear from here. So this is your PL inequality, right? So there, I mean, on it, so either the minimizer is unique or you have a constant function. So these are the only two possibilities. I mean, we eliminate the trivial case, so we assume that, we are working with unique minimizer. All right, so we have this as your PL inequality. Okay. So let's now define another function g of x as square root of f of x minus f star. Is g of x a valid function? Is square root well defined here? Right, because f of x is always going to exceed f star. So this is a positive function. And since f satisfies PL inequality, so this implies f is an invex function, and g of x is simply defined by offsetting f of x and taking the square root. So you also conclude from here that g is a positive invex function. I mean, invex is not as much important as the positive part in this, that g of x is always going to be positive. Okay, so that's one thing that we need to keep in mind. So what is gradient of g of x? That's going to be gradient of f of x okay. Is this clear? And what about the norm of this gradient? That's going to be the norm of this gradient of f of x. So if I take the square of it, it will be square of this thing, right? Which is and here I can use PL inequality on f, right? I can use this 1, which would be greater than or equal to mu over 2. Okay. The result that I have gotten is okay. So before we proceed further with the proof, why do you think we have defined the function like this? Because we want to show this quadratic growth, right? So that means g of x is greater than or equal to square root mu over 2 times x minus x star is what we want to show. Okay, that's one of the reasons why we have defined the function this way. The other thing is, somewhere we had to use a PL inequality, and that is used to show that this particular term is greater than or equal to mu by 2. Okay, all right. So now let's consider a gradient flow. Suppose we run this gradient flow. X dot is negative of gradient of g of x. Okay, suppose we run this particular gradient flow. So this would have its own x as a function of time, right? Like if you simulate this particular flow. So what would be g of, let's say you start at x naught, and at any time t, g of x t, what would this be by definition? Okay. So this is just like if you integrate gradient of g of, basically this particular term, that's what you are going to get, right? We are looking at x naught, g of x naught minus g, right? So which is same as, let's call it t naught or even 0. Let's say t naught is equal to 0. It doesn't make a lot of difference. Okay. So this is nothing but minus 0 to t gradient g of x dot dt. Is everyone with me on this? So what is gradient x dot for this particular flow, negative of gradient of g of x. So that means g of x naught minus g of x t is 0 to t. Okay. And from equation 2 or inequality 2, we have this constraint on gradient of g of x square. So this is greater than equal to mu t over 2. Okay. So what do we know about this particular function g? G is a positive invex function, right? So from here we have g of x t, which is less than equal to g of x naught minus mu t over 2. That means there must exist a finite time when x of t basically becomes x star, right? Okay, because this function, the minimum value of this function is 0. So there exists a finite time when this function, this x of t becomes x star. So let's say that finite time is capital T. Since g of x t is positive, or rather non-negative, or in fact, I mean otherwise, yeah. So there exists some time t, finite time t, t less than infinity, such that g of x t is g of x star, right? Because at x star g of g is 0. Okay. So now we have to somehow, so we now have, obviously we are going to integrate from 0 to capital T now, because, so what is the length of a path that, like if let's say if I try to basically find the length of the trajectory starting at x naught and ending at x star, what should that length be equal to? Dx. So basically, actually it's a modulus of dx, right, because it's a length. So you can write this as x dot dt from 0 to capital T. Okay, length of the path traced by this particular dynamical system. Okay, and what is x dot by definition? Gradient or negative of gradient of g of x. So and we know that this length is always going to be greater than or equal to if I join these 2 points by a straight line, right? So that means x naught minus x star. Okay. The straight line distance between these 2 points is always going to be less than or equal to the total length that is traced by this particular dynamical system, or length of the path traced by this particular dynamical system, right, starting at x naught and ending at x star. So let me call this as x naught x star, so that it's also clear that we are looking at the length from x. So let's call this equation or inequality 3. Okay. So if I revisit this particular definition here, or rather this term over here, so g of x naught minus g x star is essentially 0 to capital T just rewriting this particular thing from 0 to capital T, which I can write this as 0 to capital T gradient of g of x dt. So from this one inequality 1 or rather inequality 2, gradient of g of x is greater than or equal to square root mu by 2. So we can write this as okay, and that's where we can use this inequality 3, which is, so this is from 2 and this is greater than or equal to square root mu by 2 x naught minus x star. This is from 3. Okay. What is g of x star, by the way? 0, right? G of x star is 0. So that means g of x naught is greater than or equal to square root mu by 2 x naught minus x star for every x naught, right? And if I just write g of x in terms of f of x, so this is nothing but saying that f of x minus f star is greater than or equal to mu by 2 x minus x star whole square, and this completes the proof. Okay. So, having a PL inequality with some modulus mu, that means a function at least has some quadratic type of growth. So, that is why you can also accelerate optimization of functions that satisfy PL inequality, even though those functions may not be convex, but because they have this quadratic kind of, like they are lower bounded by this quadratically growing function, you can also accelerate optimization of such functions. Is this clear?
But in invex function, there might be studied local minimum.
No, there is no local minima, right? So, invex function also have unique minima either, but they may not be convex. So, this is an example. So, we looked at one particular example, right? X square plus 3 sine square x. So, this is not strongly convex because of this. In fact, this is not even convex. This is, the function looks almost like this. But if you look at the, basically this particular function satisfies PL inequality.